Hello, everybody. Today we're going to work on pages 5, 6, and 7 in the unit packet. I've attached these pages of the unit packet to the Google Classroom, so go ahead and download them and print them out and take notes as we go through these pages. I've also loaded a video on the notes for this part of the chapter, so you should look over and study that video before watching this video. So let's get started. I'm going to get rid of me right now. There we go. Okay, here we go. Define electronegativity. The ability of an atom to attract bonding electrons. So the idea is that if you're in a covalent bond, it's the electron pairs that are holding these atoms together. Now, one atom may have a higher ability to attract the electrons to another. What that does is it causes the electrons to hang out closer to that particular atom that has the stronger pull. Electronegativity is a periodic property. Describe the trend in electronegativity for moving across a period on the periodic table. The electronegativity increases from left to right, GHT across the periodic table. And you can see this. I'm going to bring up a periodic table. So what happens is, as you go across the period, the electronegativity increases. As you go from bottom to top, the electronegativity also increases. So you can see that as you go from the bottom left to the top right, it gets bigger. Okay. Let's go back to our lecture. Okay, the electronegativity of an element describes the tendency to hog electrons or to attract electrons in a bond. The ultimate electron hogs tend to not even to share their electrons with other atoms, but rather they steal them and they hold on to them completely. This affects the tendency of a bond to become more ionic, where the electrons are completely transferred, and less covalent, where the electrons are shared. The greater the difference in electronegativity, the greater the ionic character of the bond. Based on this principle, use the electronegativity chart in the textbook to identify the following bonds as being more electronegative or less electronegative, using these diagrams on the next slide. So here we are. So what we have down here is diagrams of the molecular orbitals, or where the bonding electrons hang out in 2 dimensions. I'd like to do this in 3 dimensions, but since this is a 2-dimensional screen, what you do is you take the 3-dimensional object and you make a slice through it. So you can see that this first one right here is 2 atoms. We got 1 atom there, and we got 1 atom there. And then in between them, we have where the electrons hang out, which is called an electron cloud or an orbital. So somewhere inside this cloud, you have the 2 bonding electrons. Let me get rid of these. Okay, so what we're going to do is we're going to do a little bit of math. What we have here are the electronegativity values for various elements. So let's go ahead and determine the electronegativity difference, and then we'll use our chart to determine what type of bond, either stronger or less electronegativity difference that these bonds have. So carbon, you can see that the carbon is right here. It has an electronegativity of 2.6. Hydrogen is right here. It has an electronegativity of 2.2. So I'm going to take 2.6 minus 2.2 equals 0. 2.6 minus 2.2, 0.4, right? What about the carbon-carbon bond? 2.6 minus 2.6 equals 0. Carbon-nitrogen. Nitrogen is 3. I want a positive number, so I'm going to put the 3 first. 3 minus 2.6 equals 0.4. Carbon-oxygen. Oxygen is 3.4 minus 2 oxygen, carbon, 2.6. What does that equal? That equals 0.4 plus 0.4 is 0.8. And then finally the carbon fluoride. So fluoride is 4. Again, I want a positive number. 4 minus 2.6, and that equals 1.4. 1.4. Okay, so here are the values. So the first molecular orbital, you can see that it's balanced between the two. So this would be one atom and the other. So if it's completely balanced, if everything is equal, we must have the carbon with a carbon. Okay. The next one is the most distorted of the bonding arrangements. So what is the highest number? Right here. This is the highest number right here. So this must be a carbon, has the lower electronegativity, so it must be on the left. And then the fluoride is on the right. It has the highest electronegativity. This one is just slightly distorted to the right. This one is a little more distorted to the right, and this one is actually distorted to the left. So which one is distorted to the left? Well, it must be the one that has a higher electronegativity on the left, and the only one that I see up here that has that is the carbon-hydrogen bond. So this must be carbon-hydrogen. So we've got that one. We've got that one. We've got the carbon-carbon. Okay, two choices here. We got one that is slightly distorted and one that is distorted a little bit more to the right. So this must be the carbon-oxygen. And that one must be the only one remaining, which is the carbon-nitrogen. Okay, let's try another slide. Okay, here is the graph that shows what type of bonds you have depending on the electronegativity difference. So in this exercise, based on the electronegativity difference, we will predict what type of bond it has. So let's go ahead and zoom in a little bit. See if I can get this right. That's pretty good. Okay. Now, so here's an example. Carbon-hydrogen, as you, on the other page, carbon had an electronegativity of 2.6. This one says 2.5, so I need to change that, 2.6. Okay, 2.6 minus the electronegativity of element B, which is hydrogen. I think it's supposed to be 2.2. Okay, 2.6 minus 2.2 is 0.4. Where's 0.4? Non-polar covalent. Okay, let's try another one. Carbon-carbon, that's 2.6, 2.6. If we subtract those, that equals 0. So that would be, again, non-polar. Carbon-nitrogen, 2.6 minus nitrogen, which I'll go to the last slide just to see what it is. Nitrogen, what was it? 3. Okay. Nitrogen was 3. 2.6 minus 3 is negative 0.4, but I'm going to take the absolute value. Remember the absolute value? Makes it positive, equals 0.4. That's below 0.5 down here, so we know that it's also it should be non up there, polar. Okay, I'm going to do one more, and then I'm going to let you guys fill out the rest of these. So what about sodium and chloride? What about those two? Okay, here's sodium is 0.9. You can see it right here. Sodium is 0.9. And then if we slide this over, we can see what chlorine is. It's 3.2. Okay. So sodium is 0.9. Chlorine is 3.2. If you subtract those and take the absolute value, that equals 3.2, 2.2, that equals 1.2. Or 2.2, right? That equals 2.2. So that is ionics because it's above 2.1. That is ionic. Okay, so here what we're doing here is we're using math to investigate this phenomena called ionic, covalent, or chemical bonding. Okay, let me make this a little bit smaller. Describe the difference between a purely covalent bond and a polar covalent bond. A purely covalent bond is when the bonding electrons are shared equally. So if the atoms are the same, for example, a carbon and another carbon, if these atoms are the same, then we know that these two bonding electrons between them, they're going to exist in a cloud that is equally shaped between them, and that is purely covalent. Polar covalent, on the other hand, for example, remember we had a carbon bonded to a fluorine. In a polar covalent, then the electrons are going to be closer to one of the atoms, and we get a distorted molecular orbital. And again, this is a cross section. So what that does, so this would be polar covalent. What that does is it pulls the electrons closer to one of the atoms, in this case the fluorine, and then that gives that fluorine a slightly negative charge. And because the electrons are being pulled away from the carbon, that gives the carbon a slightly positive charge. And that makes one side of the molecule, one side of the bond has a higher charge, or a lower charge, in this case, a negative charge, than the other. And that's like a little tiny magnet. And we call that a polar bond. So it's polar. Just like the Earth has a north and south poles, we have polar bonds. Okay, I think that I'm going to take a look at my time here. Yeah, I'm going to stop it here because I'm already exceeded almost 15 minutes. So we will continue on in the next video. So have a good evening. I hope you enjoy these videos and you're getting something out of them. I'll talk to you on the morrow.